Now let's try to understand how an RL circuit will behave when the switch B is closed. Now in the first part what we did is that the switch A is closed. When switch A is closed, then this circuit, it will behave like this. And when switch A is closed and time is infinite, the current is maximum. So a maximum current is flowing through this circuit, and the direction of current will be this, and the current that will flow will be maximum current, and it will be epsilon upon R. Now what we are going to do is that the switch A is open and switch B is closed. So it means that when it is charged, when the maximum current is flowing through this through this inductor, then now we open this switch and we close this switch. Then it means that now there is no battery here, and we are now trying to close this switch. So and the current is flowing in this direction. So there is a current flowing, which is a maximum current, which is flowing through this inductor. Now when the switch A is open and B is closed, it means that there is no battery. There is no battery in this circuit, and when there is no battery, it means that whatever the current will be, it will start to decrease, it will start to fall out. Now we know how an inductor will behave. Now if the current through the inductor will start to decrease, then it means that the magnetic flux will also start to decrease in the inductor. So if this is how the current is, then the magnetic field in the inductor will be in this direction. Okay, so this magnetic field in the inductor, it will start to decrease. So when it will decrease, an EMF will be induced, which will try to oppose the decrease in current. So it will behave like a battery, which will try to enhance the current. So it will behave like a battery in this direction, because it will oppose the decrease. It means that it will try to increase the current. So it will behave like a battery, such that the positive will be in this side, so that the this current is flowing in this direction, and this battery will also have a current in the downward direction. So now this will be our circuit. And now again we know that this battery is a bad battery. So if we have to draw it with time, so initially it will behave, the inductor will behave like this, but finally it will behave like this, and there will be no current. Current will die out completely. Okay, and so let's say that because it's a bad battery, so at time 0 the current is maximum, because we are starting from this situation. Okay, maximum current is flowing through it. As time increases, the current has decreased, and at time infinity the current has decreased further, because there is no battery, external battery in this circuit which can supply the potential difference. So it will tend to have zero current at infinite time. So if I have to repeat it again, the current is flowing, but because there is no battery, so the inductor will try to oppose this decrease, so it will try to increase the current. So it will behave like a battery which is having minus in this side and plus in this side. Okay, so and here this battery, it has some potential drop epsilon L, and here it has some potential drop epsilon L, and here it will also, now because there is no battery here, so it, and there is no current here, so we need not talk about it. And this potential drop, let's say that this is dash, so epsilon L dash will be greater than epsilon L, because it's a bad battery, and so it tends to decrease the potential drop as we move with time. So let's try to understand this circuit, and we'll write an equation for this one, which is Kirchhoff's rule, loop rule. Total potential drop should be equal to 0. Now the flow of current is in this direction, so because of this we'll have a plus here, minus here, plus here. Okay, so if we write this equation, so let's move from here to here, so it will be plus to minus, so minus IR, and then from minus to plus, so it will be plus epsilon L will be equal to 0. Okay, or minus IR minus plus L di upon dt will be equal to 0. Now in this equation we need to understand something. This current di upon dt is a decreasing current because the current is decreasing. Okay, so di upon dt should be negative. Why? Because when we're talking about the first case, when we used this inductor, and this inductor, it behaved like a battery when A was closed, we're talking about this. Then at that time we had an equation where this current is flowing in this direction. Then epsilon minus IR minus, because it was behaving like a battery, which is plus this side and minus this side, so it was minus L di upon dt is equal to 0. In this relation, di upon dt, it is not a decreasing current. The current was increasing. If you remember this one, when the switch A was closed, then the current was flowing in the clockwise direction, and the current was increasing. It increased from 0 to I to some maximum value. So the current is increasing in nature. So di upon dt, it was increasing. So if increasing was positive current, then in this case, if the current is decreasing, in our case the current is decreasing because it's going from maximum to 0. It's a decreasing current, so we give it a negative sign. Okay? So then this equation will become minus IR minus L di upon dt will be equal to 0. So this will be our equation, and time will vary from 0 to t. Current will vary from I maximum to I. So let's try to solve this equation. So we have this equation, minus IR minus L di upon dt is equal to 0. So then we can also write it as minus IR is equal to L di upon dt, or we can also write it as minus R upon L dt will be equal to di upon I. Now we're going to integrate it, this, and we know the limit of integration has to be from 0 to t. If the time is varying from 0 to t, the current is varying from I maximum to I, to some value I, which is varying with time. So it will be I maximum to I. So what we get from here is RT upon L should be equal to log of I where it will be I maximum upon I. And you know what I maximum is? I maximum is epsilon upon R. So this is the maximum current. So it will be log I minus log I maximum, or log I upon I maximum. So we can also write it as exponential minus RT upon L will be I upon I maximum, or I will be equal to I maximum exponential minus RT upon L. Okay, this is how the current will behave. Or we can also write it as epsilon upon R exponential minus RT upon L. So this is how the current will behave. Now let's try to find out the value of current in different times. So if time is 0, current will be equal to epsilon upon R exponential 0. So it will be epsilon upon R, which is the maximum current. So initially the current is maximum. So at time is equal to L upon R. So current will have a value of epsilon upon R exponential minus 1, and at infinite time current will have epsilon upon R exponential minus infinity, will give you 0 current. So if you have to plot it, it will look like this. At time t, current, so it will have, at time 0 it will have a maximum current, so it will be I maximum, and then it will decrease exponentially, so it will decrease exponentially, and at infinite time it will tend to 0. So the current will decrease gradually as in the inductor when there is no battery in the inductor, when the battery is removed from the inductor. Okay, so at that time the current will decrease gradually, and this is how the current will behave. Now this time L upon R is called tau, or the time constant of a circuit. Okay, it is time constant and it is given by tau. So that is why this equation can also be written as I is equal to epsilon upon R exponential minus T upon tau, and it has units of seconds. L upon R has units of seconds.